Okay, so here we've got an unidentified compound. We've been told it contains carbon and hydrogen. And we've been asked to figure out, well, what's the empirical formula of this compound? So how am I going to approach this? Well, firstly, we've got the percentages by mass in the question, right? So we've got the 94.74 and the 5.26. Based on some of the subsequent steps of how I would like to approach this, I'm going to do a check. So I'm going to check, well, what do those percentages add up to? I'd invite you to have a go adding those up, see what you get. Ideally it should be maybe 100, but if it's not, that's fine. We can do some make some assumptions, do some rounding later on. But okay, so 94.74 plus 5.26, right? I mean, based on visual inspection, you can kind of see what it's going to end up as, so if you did have a go, you should find that comes to 100, right? And so that's fine. It's 100. Now we're looking for the empirical formula, which we know to be the simplest whole number ratio of the elements present in the particular compound. Now, or should I say the atoms of the elements present in the compound? But in any case, what do we actually need to do here? Well, we need to find out that ratio. But what we have so far is percentages by mass, which, although it gives us some level of quantitative perspective, it's not a very easy way to compare the two elements, because, as we would know, these two elements have different relative atomic masses. So to compare them by mass, it's not as straightforward to do directly. So what are we going to do? What we're going to do is we're going to try and find a way to convert these to amount of substance-based comparison factors, ratios effectively, right? So how are we going to do that? Well, we're going to leverage the equation moles N is equal to mass divided by molar mass, right? That's in grams, and that's in grams per mole, right? And what do we do with that? Well, effectively, we need to get the actual relative atomic masses from the periodic table, right? And so here, so what we've got carbon and hydrogen. So hydrogen here, carbon here. Now what we know is that the relative atomic masses effectively would be the molar masses, right? So effectively for the hydrogen it's going to be 1, for the carbon it's going to be 12. So I'm just going to write this down here just to kind of make clear what my working is, right? So and in this case, MR is going to be, as you saw previously, it's going to be in grams per mole, right? So it's going to be in, just write, it's going to be in grams per mole, right? And so for MR of carbon is going to be 12. MR of hydrogen is going to be 1, right? I mean, these are common, relatively quite common elements, so you may have known that already. So anyway, so what we're going to do is we're going to make an assumption, and this assumption is going to enable us to effectively calculate the empirical formula. The assumption we're going to make is we're going to assume that the specific sample that we have is a total of 100 grams, right? And by doing that, what we're going to be able to do is effectively take these percentages by mass and convert them into actual masses, right? And that's going to effectively enable us to use this equation. So therefore, based on that, we can say for carbon, it's 94.74 grams, and for hydrogen, it's 5.26 grams, right? And as we saw here, to get to the moles, we need to divide the mass by the molar mass. So we're going to do that now. So we're going to divide these masses by the molar masses. So divide this by 12, divide this by 1. And once we've done that, what ratio are we going to get? So for the ratio of moles, in this case, we know that that's just going to be 5.26, right? Because we're dividing it by 1. For this, I would invite you to have a go on your calculator and see what value you get, right? Okay, so if you tried that, what you should have found, or at least what I found, was this would come to 7.895, right? Okay, so we've got 7.895 to 5.26. None of these are a whole number. And remember, we need the simplest whole number ratio, right? So what we would want to try and do is get both of these to a state where the ratio actually is between two whole numbers. And one of the ways I'm going to do that as a first step is I'm going to force one of these numbers to become an integer value. And the way I'm going to do that is I'm going to divide both sides by the smallest number. So I'm going to divide this by 5.26. I'm going to divide this by 5.26, right? Now again, on this side, it's quite straightforward. You don't need a calculator, but because you're dividing something by itself, you're just going to get 1. But on the other side, you can have a go on your calculator, see what you get from doing that. I'm going to give my answer here for this step to 5 decimal places, which gives me 1.50095, right? And as we can see, this is, I mean, it's still not particularly close to a whole number, right? At least with respect to carbon, even though we've got a whole number corresponding with the hydrogen at this stage. So what I'm going to do is a scale up process. So I'm going to consider, well, if it gets multiplied both sides by 2, maybe by 3, maybe by 4, effectively stopping when it works. I'll see when do I actually get a whole number on effectively this side. This will obviously, I'm multiplying this side by integer values, so of course it would be a whole number in each of these cases. So we're really focused on trying to solve for this issue corresponding with the carbon. From visual inspection, you could probably infer what we really need, but nonetheless, let's multiply both sides by 2 to start off with, and see what we get. So if I multiply this side by 2, I'm going to get 3.0019, right? And when this is compared with this side, well, of course this is going to be 1 anyway. And okay, so if we look at this now, looking at it from a perspective of, well, what is this to 2 decimal places? Is it an integer value to if we round it to 2 decimal places, do we get integer values on this side? And the answer now would be yes. Like if we round it even to 2 decimal places, it comes to 3, right? And of course, therefore, to 1 decimal place, it's also an integer value. And so that's what I'm going to do. I'm going to round it, and because the 2 actually got us to this point, we don't need to proceed to multiply by 3 or by 4 or by 5. We've already got to effectively what we were trying to get to. So this is going to be 3.00 corresponding with 1, right? And therefore, no, wait. I can't believe I did that. Yeah, no, this should be, yeah, that should be a 2. Yeah. Yeah, so that should have been 2. Multiplying both sides. Yeah, so that should have been a 2 from at that time. I was mainly focused on this side. But yeah, so that's a 3 to 2. And this effectively gives us what? It gives us a 3 corresponding with the, so this is going to be C3, and on this side it's going to be H2, right? And what that effectively gives us is, so C3H2. One of the things you may want to look at is a molecule. So before I actually go into that, this is effectively going to be, in this case, our empirical formula. Okay, so this is the simplest whole number ratio. As you can see, there's not really something we can divide this by, whereby we would still get a whole number ratio. If we divided this side, for example, by 3, okay, you might get C1, but on the other side, you're now going to have a value which is not an integer, right? And the same on the other side, you divide H2 by 2, okay, you might get H, but then on the other side, you're going to get, actually, well, we're going to get 1.5, right? So corresponding with the carbon, so that wouldn't work either. So we can say that this is our simplest whole number ratio, right? Okay. So the other thing which we're actually going to look at is just consider, well, this is less about empirical formula, it's more of just a topic of interest if you want to look into it. So this is called cyclopropionylidene, right? So right. I'm not gonna go too much into what this is, but you can look into this if you want in your own time. It looks something like this. So it's like carbon, carbon, carbon. You've got hydrogen. And if you look at the actual, and just for clarity again, this is, of course, this is an empirical formula. It's not a molecular formula. But if we were, for the purpose of example, to assume, okay, imagine if it was a molecular formula, what structure could it have? This is an example of one of the structures it could have. And this is quite an interesting molecule in some sense, in that it's, if you're interested in stuff like astronomy, I guess, it's something which is found around Saturn, for example, like one of Saturn's moons. But anyway, you can look into that in your own time. But yeah, so this in this case would be the empirical formula. Okay.